Hey guys, it's nice to chat with you again. I'm about to go through the 2012 problem, the question number 2 from our AP free response packet for Unit 5. So as a reminder, this is the packet that we're working on right now. A couple of videos have already been put up for you guys, but this is our next one, so we're going to go through 2012. So let me just start by reading the problem. It says, let R be the region in the first quadrant bounded by the x-axis and the graphs of y equals ln x and y equals 5 minus x as shown in the figure above. Before we even get into the subpart, it's good to remember this is question number 2. So I know that this is a calculator problem, which is great. So I've got my calculator here and ready to go. This is a calculator problem, so we could figure out which one of these is ln x and 5 minus x using our calculator, but it's a good thing to talk about just to remember how to identify curves by their shape. So if you didn't have your calculator, let's think about this really fast. Y equals ln x. If you think back to Algebra 2 and our function families, I'm just going to go up here real fast and say if I have the function y equals ln of x, I know that's in the logarithmic family. And logarithms have vertical asymptotes at 0 and they come up, they cross through a value of 1. This should be a quick reminder that remember ln of 1 equals 0. So that's the shape of my natural log function. So you can see this right here is going to be the natural log. So I'm going to write here real fast, y equals ln of x. And then we know that this is going to be a straight line. Specifically, if I did have to grab this, I have y equals 5 minus x. I know this would cross at 5, that's the y-intercept, and then it has a slope of negative x, so it would come down like this, and it would actually cross here at 5 as well. So this thing here is my line y equals 5 minus x. Okay, so let's see what part A says. It says find the area of A. Oh, sorry, find the area of R, so R is this region here. Well, we have a couple of options on how to do this. We know from class that to find the area between curves, we're going to integrate the top curve minus the bottom curve. But with this problem, we actually have 2 ways to approach this. We can do it with respect to x and do top minus bottom. The only problem is if I do top minus bottom, my top changes. Here my top would be ln of x and my bottom would be 0. Here my top would be 5 minus x and my bottom would be 0, but I'd have to write it as 2 different integral expressions because my top is changing for these 2 parts. The second way I could do this problem is do my left-hand turn that we've talked about and do things with respect to y, because when I turn my page this way, I can see clearly that this is the top and this is the bottom. However, if I'm going to do things with respect to y, I do need to rewrite these equations. So why don't we do that quickly so we have it ready for us if we choose to do this. If I solve this for x, I'm going to have to do e to the on both sides. So I end up with x equals e to the y. Over here, if I solve, I would add x over to this side to get it by itself and make it positive. I would subtract the y over. So I end up with x equals 5 minus y. So those are 2 different ways that I can write those curves. Okay, I'm actually going to do part A both ways so you guys can see. But regardless, I'm going to need my bounds for my integral, which means I'm going to need to know what the x and y coordinate of this point is. So let's go into our calculator. I've already gone through and done some of this, but let me go into y equals, and you'll notice that in my y equals, let's see if you guys can see this okay. There we go. In my y equals, I have ln of x and 5 minus x. I want my window to be appropriate for this problem, and you'll notice they've already given us pretty good window here. So in x, I'm actually going to go from -1 until, this is 5, so I normally go to about 6, and then I'm going to go from -1 to about 2 or 3. So in my window button, you can see that I've already adjusted my window. And a minimum side to side, I should see 0 to 5, and then up and down, I should see 0 to 2. I like to go a little bit farther, I just find it helpful. Okay. So when I go ahead and go and graph, here are my 2 curves. I need to find this intersection point. So as a reminder, I'll go to second calc intersect. I need to scroll to that intersection point. You can see that little box there. I'll scroll over and back so you guys can see it. So I want to go to as close as I can at point of intersection. I'm going to have to push enter 3 times. So 1, 2, 3. And there's my intersection point. So I'm actually going to start by just writing down those values. I have both the x and the y coordinate for that intersection. So for my intersection point, what I have is 6, 9, 3, 4, 4. If I don't store this in my calculator, I want this to at least 4 or 5 decimal places. I tend to go to 5. Okay. And then my y coordinate is 1.30655. Remember, if I'm going to use these values, the answer of like part A, B, and C have to be exact to the thousands place. So I often need to make this to a further place to make sure if I'm using a rounded value, my final answers are exact. Now, we've talked about in class how we actually want to store these values in our calculator. So if this is the last thing that I've done, and I go into my home screen and I push store, it's going to take that X value, that that intersection point, and store it in my calculator. I'm going to put it in as A. So you'll notice A is now this value that we found for the X coordinate. And if you want to compare real fast, there's my X coordinate. And that's what we saw on the previous page. Okay. I also want to store that Y coordinate. Well, remember that intersection point is occurring where ln of x equals 5 minus x. So I'm just going to plug the coordinate into this to get that y value real fast. So I have ln of this. And that's that y coordinate from the intersection point. If you want to compare it real fast, you can see that they're the same. I'm going to store that in b. So store alpha and then b. I just want to make sure they're in different letters. I'm not writing over A or B. Okay, so I'm actually on my paper going to write this down. So this is A and this is B. As long as you define those values, we can now use A and B for the rest of our problem. We don't necessarily have to write these values out each time. So now let's actually jump into starting to write an integral expression for part A. And I told you guys I'm going to do A two different ways. And if you want to skip through one or the other, that's totally fine, but I'd like to provide them both for you. So find the area of R. I'm going to start with top minus bottom with respect to X. So as I go from 1 until this intersection point A, so if I integrate from 1 to A, I'll have top, which is ln of X, minus bottom, which is 0. I have to write that dx. Plus, I also need to find the area from A until 5 of top minus bottom. Well, top is 5 minus x. Bottom is 0. I don't have to write that, dx. Okay, so there's my integral expression. I'm going to type that into my calculator now. So I'm going to have the integral, so math 9, from 1 to A of ln of x dx plus, I'm also integrating from A until 5 of 5 minus x dx. And there's my answer. Something we haven't talked about a lot in class is we know we have to round to the thousands place. If you want to, you can actually write out to the 4th decimal place. They will only read through the 3rd decimal place. So if you're ever concerned, you can also just write out 4 digits. So now let's do this the second way. First we did it as top minus bottom with respect to x, but now I'm going to do the problem as if I had done a left-hand turn. So if I do the left-hand turn, we can now say that that line is my top curve, this curve, which was ln of x, or e to the x equals e to the y, is my bottom curve. So now I'm going to write it this way. I'm going to integrate. Now I'm doing it with respect to y. So instead of going side to side from 1 to 5, I'm now going up and down from 0 until intersection point B. Okay, that's the y coordinate. So I would go from 0 to B of top minus bottom. Well, top is this line if I do my left-hand turn, but I have to do things with y, so I'm going to have 5 minus y minus the bottom, which is e to the y. And I'm doing this with respect to y. So if I type this into my calculator, I make it so you guys can see it. I'm going to have math 9 from 0 to b. I've got 5 minus y, we'll have to type that in as an x, but that's okay, minus e to the y. Okay, and push enter, and I should get the exact same answer. So you can see that either way that I do that, I'll get the same answer. It's just 2 options for how to do the same problem. One requires you to set up 2 integrals, and one requires you to solve things for y. So either way, you're going to get the same thing. Or I shouldn't necessarily solve for y, but you have to find things with respect to y. So now let's move on to part B. I guess I didn't need all the space, but I'll move down here anyways. Okay, part B says region R is the base of a solid. For the solid, okay, here's my key word, cross-section perpendicular to the x-axis is a square, right? But do not evaluate an expression involving one or more integrals that gives the volume of the solid. Okay, so we've got some key information here. We're doing cross-section problems. Well, we know for volume by cross-sections, we're going to integrate the sum, or we're going to integrate the value of the area of a cross-section. What we're really doing is adding together a ton of little slivers that are areas that are going to build together to create a volume. We know it's perpendicular to the x-axis, so if I were to draw in these little like these cross-sections, they would look up and down like this. Okay. So we're doing it for squares. So if I'm integrating the area, the formula for the area of a square is going to be side squared, which means I need to know the length of S, or one of the sides. So this line here is going to represent the length of S. Okay. And notice we only have to write, we're not going to have to evaluate this integral expression. Well, the problem that I have with going side to side like this is that my S value is changing. So from 1 until A, my S is going to be represented by this top curve, ln of x minus 0. But after I get past this point A, my top minus bottom is changing again because my top is now this line, my bottom is 0. So like I did for this part in part A, I'm going to have to write this as two separate integral expressions. And they gave us kind of a nice little hint here with one or more. So if I go into part B, I'm going to move this down so you guys can see a little bit better. And I'll just sketch the curve real fast since we can't see it anymore so that you guys can see what it looks like. Remember, I'm going from 1, and then I've got this line here. So this is 5, this is 1, this was ln of x, and this is 5 minus x. Okay, so the first set of cross sections I'm going to do is I'm going to integrate from 1 until A. Okay, I need to integrate area. Well, area is side squared. For this part, the value of S of top minus bottom is going to be ln of x minus 0. So S is ln of x. We want area, so it's side squared. So that's what I'm integrating for this first part. Plus, now I also need to do the cross-section volume from here over. So now this represents S. Okay, so actually let me write this from earlier. This S for the first part was ln of x. This S for the second part is top minus bottom, so 5 minus x minus 0. So I'm now integrating from A until 5. Side is 5 minus x, but we're integrating area, we want side squared. So those are my integral expressions that represent the volume of the entire figure when I do cross sections that are squares. Okay, so now let's look at part C. Part C says the horizontal line y equals k divides R into two regions of equal area, right? But do not solve an equation involving one or more integrals whose solution gives the value of k. So notice it says there's a line y equals k that divides this section into regions of equal area. So I'm going to just draw on this line real fast. And we need to figure out, we're not actually going to have to solve it, but we're trying to create we want to put this line in a place where the area of this region down here is equal to the area of this region up here. So really what I want to do is set up integral expressions that state that this area is equal to this area. Well, I'm going to have to integrate top minus bottom to get area, and it's just going to be a lot easier if I think about it looking this way so my tops and bottoms are consistent. I want to integrate the top curve minus the bottom curve from 0 until k, and then I also want to integrate top curve minus bottom curve from k until this intersection point. Well, the y value, the y part of the coordinate was b, so I'm going to go from k until b. I want those two areas to be equal. So if I go down here to part C, I'll draw that picture again since I can't see that top anymore. So I have this thing going on here. Curve, I've got a line, this is 5, 1, this is A and B, and I have this line in here now, K. Well, we said it's easier to do top minus bottom if we do the left-hand turn, so we do the curve, we're going to do things with respect to Y. So let me write these integral expressions. So I'm going to start with this area for this bottom portion. So I'm going to integrate, remember I'm doing things with respect to y, from 0 until k of top minus bottom. Now notice these things are all y's. I had to use the thing where at x equals, so the things were with respect to y. Okay, so that's going to give me the area of top minus bottom for this piece. And this needs to be equal to the area of this piece. So I'm going to go from k until b of top minus bottom. And this is my integral expression. They didn't ask us to solve for k, they just asked us to write an integral expression that would allow us to solve for k. So there's my integral expression. So there's two things I want to talk about before I end this video. The first is there's actually a second way to think about part C. If you did actually have to solve, it would be helpful. So let me talk about that really fast, and then I'm actually going to just show you guys the pointing on how the AP would point this problem. So another way to do that, we actually know the volume for this whole area. So another way to set up this problem would be that the integral from 0 to k of this so in other words, the area for this is equal to half of the total area. If you actually had to solve for k by hand, this could be an easier thing to work with. We have one less integral, and we can actually integrate this by hand because we get 5y minus 1/2 y squared minus e to the y, and you'd plug in 0 to k and solve. But that's just another way to think about this problem, and this would also have been correct as well. So let's look at pointing really fast for parts A, B, and C. Let me pull up my scoring guideline real fast. One moment, please. And guys, remember, you can pull up these scoring guidelines online anytime. So let me look real fast. Okay, so for part A, you would get 1 point for your integrand, which depending on how you set it up could be a little different. So this point, it would be like this piece here, and this piece here would be 1 point. I'm going to look at this one, it's a little easier. So you get 1 point for your integrand, you get 1 point for your limits, and you get 1 point for your answer. And the same thing would go here, but now your integrand just has pieces. Your limits would be these, and then your answer would be 1 point. For part B, you get 2 points for your integrand. So for this stuff here and this stuff here, totally you get 2 points. I don't know how they break it down. If you messed up one, if you'd still get 1 point or things like that. And then your expression for your total volume. So if your complete expression is correct, you get a point. Okay. And then for part C, you get 1 point for your integrand. Now the scoring rubric uses this part down here. You get 1 point for your limits and 1 point for your equation. So long as your whole equation is correct, you get a point for your limits. And I'm just going to write it out like this. So your limits being this piece here and this piece here, and then your integrand, you also get 1 point, which is this stuff here on the inside, okay? So I hope you guys found that helpful. I hope you guys are all doing well, staying healthy, finding fun things to do at home. Hopefully I'll see you guys all soon.